Once again, we have a boat trying to get upstream through a narrow passage where the river is going 22 meters per second. The boat itself has a maximum velocity of 30 kilometers per hour in still water and wants to know if it'll make it. Now, right away, before we get started, you should recognize that we've got mixed units here. We've got meters per second, which is what the river is being measured in, and then we've got this kilometers per hour, which is what they're measuring the boat in. So let's get those two things to match. So if I call the velocity of the boat in still water, I'll label it VSW, so your maximum velocity, still water. It's 30 kilometers per hour. Now I want to convert that to meters per second. So it doesn't matter which we get rid of first. Let's get rid of the kilometers. Now it's on top here. So place it in the bottom of my unit conversion, and I want to get meters. Here's 1,000 meters in 1 kilometer. Notice the kilometers will cancel, and now I've got meters divided by hours. So let's simultaneously get rid of the hours. Now H is on the bottom, so to cancel it off, I need it on the top of my unit conversion. Seconds should be on the bottom, and there's 3,600 seconds in 1 hour. The hours will cancel, and I'm left with meters divided by seconds, which is exactly what I want. So when I go 30 times 1,000 divided by 3,600, I end up with an answer of 8.3 meters per second. There's my still water velocity. Now the river velocity, we're going to leave because they match now, and we're going to leave it at 22 meters per second. Now let's just get this question a little bit more organized. So I've got this river. I'll just draw sort of a random river like this. There's the shores of the river. And let's imagine the river is flowing from right to left. So the river's velocity is 22 meters per second to the left. So it'll look like this, a fairly long vector of 22 meters per second flowing to the left. Now the boat is going upstream against the current, and its velocity is smaller, but it's to the right. So its velocity is only 8.3 meters per second. And we want to see what the net effect is. So like the previous question, what we're doing is trying to figure out the overall combined velocity. So we're taking the still water velocity of the boat as a vector, and we're adding it to the river's velocity to get what we call the combined velocity, which in this case we refer to as the velocity with respect to the ground. In other words, somebody standing on the shore, what are they going to see this boat do? So vector addition, when you add them, remember it's always tip to tail on our diagram. Let's see how it looks. I've got 8.3, a fairly small vector to the right. And then at the tip of the 8.3, I'm going to start the tail of my 22 meters per second. So right here is the tail of my 22, and we know it's quite long, and it's pointed to the left. So this is 22 meters per second. So tip to tail, I've successfully added these two vectors together. Now the final answer, which I'll do in pink here, always points from the start of your vector diagram towards the finish. So my final resultant looks like this, pointed to the left. And we're calling that the velocity with respect to the ground. And clearly, if I just take 22 and subtract 8.3, I'll get the magnitude of that little gap, which will be 13.7 meters per second. And you can see the direction, which is why the diagram's important, which is to the left. So the boat, which is trying to go right, ends up being dragged left by the current, so it does not make it up the stream.